I thought they were just so old-fashioned that they really didn't have any meaning or importance anymore. But here's why I cover the classical experiments, because they tell us about experimental design. And we can break these down into those simple concepts that we just talked about, where opposite charges attract and like charges repel. Okay, so our first experiment was done by J.J. Thomson. Right around the turn of the century, I want to say like 1897 or something. It's right around 1900. And probably not him, let's be honest. Probably his grad students and postdocs, right, did the experiment. And they took a cathode ray tube, which is just an evacuated glass tube that has electrodes, basically. So like a positive plate and a negative plate. So we'll just think of it as an empty glass tube. And it had positive at one end and negative at the other end. We're going to simplify it a little bit. So their experiment was they populated or they filled this glass tube with different gases, one at a time. So like they filled it with helium gas. They flipped a switch to activate the charge on these plates. And here were their observations. And then I will tell you their conclusions. Their first observation was that there were rays in all the gases they tried. When they flipped this switch, they saw these weird rays. So because they saw these weird rays in every single gas they tried, their conclusion was, whatever these rays are, they exist in all matter. It's a little bit of a stretch. The second thing they observed was that these rays bent toward a positive plate. So what do you conclude from that? If it's attracted to positive, that means it's negative. Exactly. If it didn't have a charge, it would neither be attracted or repelled. So whatever these rays are, they're negative. He did some more sophisticated experiments, which we really won't go into that much. He discovered the electron. He wasn't able to isolate a single electron. He was able to calculate the mass to charge ratio using a more sophisticated experiment. And that's the symbol for electron. It's a lowercase e with a superscript negative sign. So he discovered, and his group discovered, electrons, pieces of atoms. Atoms are neutral. Elements are neutral. If you have a chunk of iron and a sample of helium gas, they don't attract each other or repel each other. They're neutral. So if atoms are neutral and they've discovered a negative piece, there must be what kind of other piece? It's got to be positive, right? It's got to be positive. So Rutherford, so the electron was discovered first. Rutherford did a series of experiments using gold foil. He pounded it out really thin. He wanted to get a monolayer of atoms, but that's not possible to mechanically achieve. You can grow a monolayer in an ultra-high vacuum chamber, but you can't like pound something into a sheet that's so thin it's only like a layer of single atoms. That's not possible. But you can get gold foil really thin, like aluminum foil. You can get it even thinner than aluminum. And he had an experiment because he said, listen, if there's something negative and atoms are neutral, there must be something positive. So he took something called alpha particles, which are kind of big for a particle, and they're positive. All you need to know is that they're positive. And he fired them at this gold foil. And he had a detector that is a zinc cadmium screen. All you need to know is that when an alpha particle hits this screen, it flashes. So, you know, it's in the 1900s, still kind of early 1900s. So it flashes when an alpha particle hits it. So if you're shooting something positive at an atom, it should interact with this positive piece by being repelled, right? Because opposite charges attract, like charges repel. So what Thomson thought was, they called the plum pudding model, and I would think of it as an oatmeal raisin cookie. I have no idea what plum pudding is. So I would think of it as an oatmeal raisin cookie, and what they thought was there was this sea of diffuse positive charge, like the cookie part was positive, so it's weak because it's all spread out, and then the raisins are these like negative point charges, these electrons. So they thought, since you have this diffuse, weak positive cookie, when you shoot this like pretty big positive particle at it, it'll just go right through it, right? Because that weak positive charge isn't enough to like even repel. And that's mostly what happened. Like over 98% just went straight through. But there was a weird artifact. A small but significant percent was deflected. And it wasn't just deflected, but it was a really crazy angle. Like not just it bounced off some solid mass, but it was repelling. So a very small amount was hitting something positive. He discovered the atomic nucleus. He discovered the atomic nucleus, and they repeated this experiment many, many, many times because it didn't make sense. He later went on to say, this result was as unexpected as if you took a gun and shot it at a piece of paper and the bullet came back at you. That's how shocking this was. It blew everybody's mind. And based on the results, that a small amount of alpha particles were deflected, he concluded that this solid piece must be small. The other thing that the observation or the result was that because they were deflected at really large angles, they weren't just bouncing off. They were being like repelled. Based on those crazy angles, they concluded that this solid mass must be positive. So results, conclusion. Evidence, conclusion. So based on that, the nucleus is small and positive. So we found the positive piece. He knew the nucleus was made up of something positive he called protons, but there was something else in there. And he wasn't sure what that was. The mass of the nucleus didn't add up to the masses of the protons. There was something else in there. But it would take another 30 years or so in the meantime to figure that out. In the meantime, Millikan, who was a scientist working on subatomic particles as well, he designed a really elegant experiment. He was so accurate, we still use that value today. So what he did was, there's a negative plate at the bottom. He shot X-rays at these drops. Some of them picked up a negative charge. Some of them picked up 2. Sorry, you can't see that. Some of them picked up 3. The bigger the negative charge, the bigger the repulsion. So that one's probably going to go up. The ones with only 1 charge will fall more slowly. So using some calculation tools, he calculated the charge of an electron. It wasn't the smallest charge he recorded. It was actually the smallest difference in charge, which is a little bit of a puzzle. The last major discovery in this vein took 25 to 30 years after this clump. After electrons and then protons and the atomic nucleus were discovered, neutrons were discovered by Chadwick, who was actually a student of Rutherford. He was also a soldier in World War I, was a prisoner of war. And after that experience, worked in the lab, which I think is just really incredible. And this was in the early 1930s. I think it was 1932. He did a really elegant experiment where he kicked out all the protons of the nucleus and then weighed what was left. He discovered neutrons. The reason it took so much longer is because neutrons are not charged. So we couldn't play these little games of, oh, does it go to the positive or the negative plate? It didn't do anything. It didn't interact with charges. So this one took longer because these particles are not charged. So they wouldn't play. They wouldn't interact with charged plates.